Assalamualaikum. So in this video, let's discuss about X-rays. In 1895, scientist named Radition discovered X-rays while he was investigating about cathode rays. Now, let's look at the production of X-rays. The production of X-rays is the inverse process of photoelectric emission. Now, in case of photoelectric emission, we incident electromagnetic radiation onto a surface and electrons are ejected from that surface. So X-rays is the inverse. Then what we are doing is we bombard the surface with high-speed electrons. Certain portion of this, no, most of the energy is converted into heat. So most is converted to heat and some is converted into electromagnetic radiation, or it's released in terms of photons. So the idea is simple. Here we incident radiation and got electron emitted. Here we bombard an electron and emission is emitted. When high energy electron is bombarded on a material surface, X-rays are produced. So it's clear it's the inverse of photoelectric emission. Now, this is the setup of an X-ray tube. Let's understand how X-rays are produced in this tube. Before that, here we have two circuits. Here we have a supply that will run through this filament only. So here we have another circuit that is used in this X-ray tube. So I'll explain how it works. Due to this filament supply, we will have a current flow through this filament circuit. So we know that when current passes through filament, it heats up. So this is the filament. When current passes through this filament will heat up. When this heat energy exceeds the work function is the minimum energy required to eject an electron. So here, if this exceeds this work function, then electrons can be ejected from this filament. So we call this type of ejection as thermionic emissions. And when this electron is ejected due to thermionic emission, we have another supply. Here we have another supply. So this supply, this side becomes positive due to this supply and this side is negative. When an electron is ejected, it can get accelerated due to the electric field. Due to the electric field produced by the external supply. Due to this electric field, this electron gains a lot of kinetic energy. It gains a lot of kinetic energy, and when it is bombarded towards this anode target, most of the energy is converted to heat. So this heats up a lot, and a certain portion is converted into X-rays. If this continuously starts to get heated up, it might get damaged, right? So we have a separate circuit. We have a separate circuit made up of a copper rod and a coolant that will run through this tube, cooling this anode target. Okay, so that's the simple idea on how X-rays are produced. Let's go through these few points. X-ray tube is highly evacuated and contains an anode as a target and tungsten filament as a cathode. Now, why do we need to highly evacuate this cathode tube? That is to avoid deflection of electron due to collision. And we also want to avoid any ionization of molecules which will use energy. But we need a lot of energy. When there is high energy only, X-rays, more amount of X-rays can release. So to avoid the loss of kinetic energy of electron due to collision. And here, next point, the filament supply is used to heat up this tungsten filament. So we were talking about the circuit over here, right? So let's look. The filament supply is used to heat up this tungsten filament to ease the emission of electron. So this will ease the emission of electron. Such cathode is called hot cathode and the electron emission is called thermionic emission. So here the spelling has to be like thermionic. The other supply generates high potential difference to accelerate. The other supply generates high potential difference to accelerate the emitted electrons. We discuss. When the electron hit the target, most of the energy is converted into heat and remaining energy is converted into X-rays. To withstand high temperature, anode target is made up of tungsten or molybdenum. So these two materials, they can withstand a lot of heat. That is why we use them as anode target. And this anode target, it is embedded in a copper rod which is cooled by circulating oil through it, as we discussed. Let's go through the notes. We might have had an idea that X-ray is a single wavelength, but it's not true. X-ray is a range of wavelength. From certain wavelength to another, in this range, within this range, we call them as X-rays. And during the production of X-rays, we do not get a single wavelength. Instead, we get a continuous range of wavelengths. So let's look why that happens so without getting a characteristic X-ray. I mean a single wavelength. Instead, why we are getting a continuous wavelength. X-rays, it is produced in two ways. One we call as continuous X-ray and the other we call it as characteristic X-ray. First, let's look at what is this characteristic X-ray. So, these electrons are highly accelerated electrons. Therefore, they have a lot of kinetic energy. And in case of the atom, most part of the atom is empty. And therefore, these electrons may just pass through. There's a possibility where they can just pass through and as well as there is a possibility where these electrons might hit the electron in the ground level. So when this electron hits this electron, the electron is just removed and it moves away. And this electron just rebounces. So here we have an empty vacancy. Here we have an vacancy. The electron in the outermost energy level, it wants to come back down to the ground level to fill this vacancy. So when this happens, this electron has more energy, but this energy level only can accommodate a smaller energy. Therefore, the rest of the energy is released. And this type of X-rays, they have a specific value. They have a specific wavelength. So we call these types of X-rays as characteristic X-ray. When we take a certain type of metal, a certain type of anode target, when the central or the ground electron is removed and when the external electron or the outermost electron fills this gap, it always is going to release the same photon. Therefore, it is called as characteristic X-ray. Next, let's look at what's continuous X-ray. When we discuss electric field, there we discuss that how electromagnetic radiation is produced. How is it produced? It's produced when charges are accelerated or decelerated. When charges are accelerated or decelerated, electromagnetic radiation is released or absorbed. It depends. Sorry, we are talking about production of EM waves, right? So electromagnetic radiation is emitted. Now, let's look how we get continuous rays of X-ray. This electron, as I mentioned earlier, there is a higher probability that it does not attack any of the electron because most of the place is free. It can just pass through. But we know the nucleus is positively charged, but the electron is negatively charged. Therefore, when this electron is moving closer, its speed starts to increase. Why? Because electron is being attracted by this central nucleus, which is positive. So here we have an acceleration. So when charges are accelerated, they emit radiation, electromagnetic radiation. And from here, as it passes this nucleus, it tends to move in this direction. I mean, it tends to get closer, but as it is having a velocity in this direction, it's slightly deviated. And during this electron is moving further away. And when this electron is moving further away, the nucleus starts to attract. It starts to attract. Due to that, these electrons undergoes a deceleration. This electron undergoes a deceleration. So here acceleration, here deceleration. Therefore, again, it releases electromagnetic radiation. Let's say when just forget about this acceleration. When it is undergoing deceleration, when it is decelerating, it's releasing photons. Okay, because when the energy is decreasing only, it releases the energy it has, right? Due to this attraction, I'll just check and tell. But when it is decelerating, it is going to emit radiation, emit photons. So here the deceleration, it's not the same, as well as it's continuously losing its energy. Now we know that the wavelength depends on the photon energy. Wavelength depend on photon energy, and photon energy depends on how much energy the electron releases, and that depends on how much energy, how much kinetic energy the electron uh, how much energy is released. So here the electron, when it is having more kinetic energy, it can release more energy, and as its kinetic energy reduces, it can only release a few quantity of energy. Therefore, the photon energy is not the same, it's changing. If it changes, the wavelength changes, therefore we get a continuous X-ray. So if we look at the graph of intensity versus lambda, there, look, we get a continuous wavelength, and here this wavelength is due to braking radiation. We call this continuous X-ray or braking radiation. So it's just like being applied brakes over here, right? So this is continuous X-ray or braking radiation, and in between this continuous ray, we have some small spikes. We have spikes. So these spikes are due to characteristic X-rays. Now let's try to understand what is this lambda minimum. For continuous X-ray only we can get lambda minimum. Lambda minimum means frequency maximum. It's similar. So when do we get maximum frequency? When the photon has the maximum energy. When the photon has maximum energy. During characteristic X-ray, there is a collision occurring. Therefore, most of the energy will be released during collision. So, lambda minimum cannot be due to characteristic X-rays, obvious. And then we come for continuous X-ray. There is no any collision. There is only reduce in speed. So here it's possible. So let's assume that the entire kinetic energy is converted into a photon. So this kinetic energy is written in terms of electron volt. Now this is in joules, so now the units are changed to electron volt as we are discussing, as we are dealing with electrons. So here we can write HF max. As I mentioned here, we can write this one as HF max. So F could be written as C over lambda minimum. So we have obtained the equation for lambda minimum. Hence lambda minimum is the minimum wavelength continuous X-ray can have. HF max is the maximum energy X-ray photons can have. Okay, so here it's important. This is for continuous X-ray. Now let's look at two characteristics of X-ray. One is intensity, the other one is penetrating power. Now both of them depend on different factors. What's intensity? Intensity is just similar to brightness. So when will something look bright? When there is more energy or when there is more of them? It's obvious when there is more photons, then only it's more bright. Therefore, intensity increases if the number of electrons hitting the target increase. Hope it's clear. So, intensity of X-ray depend on the number of electrons hitting the target. It can be controlled by the filament current. Why by the filament current? Because here the filament current is responsible for the emission of electron. If we increase this current, then the emission also will increase. The number of electron emitted will increase. Next, we have the penetrating power. So what does this penetrating power depend upon? When the electrons have more energy, it will release photons with higher energy. So when photons have more energy, they can penetrate a lot. So penetrating power depends on the energy of the X-ray photons. F increase or lambda decrease. Any of that we can increase the penetrating power. And how to control this? This can be controlled by the applied voltage. Why? This voltage applied is responsible for the acceleration of the electron. It's responsible for the acceleration of electron, which is in turn the kinetic energy of the electron and as well as the energy of photon. If the penetrating power is high, it is hard X-ray, and if it is low, it is soft X-ray. So we have two words, hard X-ray and soft X-ray, depending on the penetrating power. Next, properties of X-ray. We know that X-rays are electromagnetic radiation. So they show all the characteristics of EM waves. They travel at the speed of 3 into 10 to the power 8 meter per second. And they have more energy, therefore they can ionize the gas which it passed through, and they can penetrate matter like wood, plastic, human flesh, etc. They can be diffracted. Diffract means when they pass along a edge, they can turn towards that edge. Not refraction, diffraction. You might have studied in waves. They can produce fluorescence. Fluorescence means when we have a scintillating material and when X-ray hits on that scintillating material, they produce fluorescence, small bright spots like. They can produce photoelectric emission. We have studied they affect photographic film, we know. They cannot be deflected. It's a property of EM wave. By electric field or magnetic field, we cannot deflect. And especially, they can be reflected, but only at very large angle of incidence. The reason is when they are incident at small angle, they will just go through or they will just penetrate that matter without reflecting. The same reason they cannot be focused by lens because they cannot be refracted for small angles. They have no mass and charge. They can cause biological changes in living cells. It's already known. So let's look at a few uses of X-ray. They are used in medicine to check tooth cavity, used to destruction of tumors, used for cancer treatment, detecting broken bones, in engineering to check cracks in mechanical parts, especially use them in space shuttle, used to detect minute cracks and folds in concretes and metal structures, to detect air pockets in metallic structures, etc. There are a lot. In customs to detect explosives, not exclusive, explosive. Explosive materials used to inspect suitcases, wooden boxes, etc. at the security centers and airports. So that's all about X-rays. Inshallah, let's start radioactivity in the next video. Until then, Assalamu alaikum.